Okay, good. So first I want to talk about the midterm. So the midterm will be, you have to read a paper. There are three choices of papers. The first one of them is essentially summarizing what Chandler's book talks about in this chapter. So in a certain sense, it's easy, but maybe not. It goes into a bit more detail, and you will see some sorts of advanced techniques over there. Not too advanced though, so it's fine. And the second one is an application of something that we will start today called free energy perturbation to drug design. How people use it to do, it's actually called computational alchemy. So it's kind of interesting. It also goes into a lot of details. You don't have to cover everything in your report, in your presentation. There will be a few things which will be a bit too complicated. I mean, you can take the time and understand those things. It's up to you. If you don't cover everything, that's also okay. And the third paper is actually a blog. The blog is by, it connects how some ideas of statistical physics are useful in machine learning, and how machine learning is trying to just rephrase some of the things that have existed in statistical physics. So I gave a choice of three papers so that if you're in biophysics, maybe you want to do the drug design part, but it's up to you. Just because in biophysics doesn't mean you have to do the drug design part, so you have at least some choice. And we will do very brief presentations on it on Zoom. So there will be two parts to get the correct grade in that. First is that you have to write a 2-page report. I said font size 11. Basically what I mean is that don't write in font size 7 and squeeze too many things there, just a decent normal font size, any font type, anything, just normal. Ideally it's a typed report, but if you don't want to type it, you want to write it on pen, on paper and take a picture, that's also fine. I don't really care. It should, however, have a diagram that you have drawn to explain the concepts of the paper. Some picture, schematic, cartoon, diagram, something. And it should ideally have an introduction section, a method section, and a discussion section. That's just a suggestion. If you think there's some other sectioning that does the paper better justice, just do that. It's totally fine. But have some sections. And that's the first part. You will have a small report, and then you will have a small presentation, 3 or 4 slides, nothing more than that. There will be 3 or 4 slides in which you will summarize what the paper was about. In these slides, you can directly use material from the paper. That's okay. You can use screenshots of figures from the papers and things like that. That's okay. You will, however, PDF your slides and email them to me. So when we do it over Zoom, I will be switching the slides on my computer. I will be sharing my screen. You will not be sharing your screen. That saves us 2 things. First of all, you don't have to worry about if embarrassing things, if anything open on your tab or shows up on everyone's screen, you don't have to worry about that. And secondly, more than that, it just adds up more time. With 18 students, 4 minutes, screen switching can easily take 2 minutes, and before we know, it's all done. And there will be 28th and 30th. It's up to you which day you want to do it. If everyone wants to do on 30th, then so be it. We will just do that. But there are 2 windows. If you want to get done on 28th, that's fine. In any case, I would like to have your slides with me before 28th, the morning of 20th. I would like to have that. And so this will count for your second midterm. If you do a good job of submitting things, in all of this, I just want to see that you're making an honest effort. Like today, 3 students didn't even bother to submit. And let's see, how many do I have now? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 2 students did not bother to submit homework. So I'm going to write to them separately and see what's going on. I mean, sure, I've told you I will give you a B+ grade, but don't push me on that. If you just stop submitting homeworks or things like that, then no, I won't give you a B+ grade. I promise I won't give you a B+ grade if you stop submitting homeworks. If you're participating, making an effort, then I will definitely give you a B+ grade. But if you simply stop submitting things, then that's disrespectful to everyone else who is taking the class or teaching it. It's not good. And if you have inconvenience, if you need more time to submit your homework due to bad internet or whatever, then just let me know. If you can't let me know in advance, let me know later. We can figure out a way, but don't just disappear because, yeah, anyway. So, and then we will have a final exam later. That will probably be, well, it will definitely be a take home. I will not be using honor lock or anything like that. It will be, I will give you 2 days, and I will try to make the exam so that you could do it in 3 hours, but within that 2-day period, you can do it whenever you want. And that will happen around the time of the final exam. Okay, so that's the second midterm, and there will be probably 1 or 2 more homeworks. Okay, so let's see what we were talking about. So before I do that, I'm going to give you a pop quiz to get your gears moving. Okay, so this pop quiz is not anonymous. I will be seeing your responses. If for whatever reason Zoom puzzles you and you're not able to submit the poll, we will figure it out later. Okay, so I'm launching the poll now, and you will have 4 minutes. Okay, there are 2 questions. There you go. Who is not able to see the pop quiz? Looks like everyone. And the first problem, yes, the democratic answer is correct. It is indeed U of R. But a lot of you fell for the garbage answers. And that's not very good, because that's where we are starting today's lecture. So let's try to understand what's wrong in the first thing. What did you do? What is potential of mean force? Potential. So let's start my Apple share again. Let's finish this one. Okay. Yeah, and Jess, I got your bonus points, 3 points. If you need it, I will definitely give it to you. If you don't need it this time, I will give it to you next time. I've made a note somewhere, so don't worry. Okay, I imagine you can see my iPad because I can also see it over here. Great. So last time we talked about that if you have 2 particles, and that's why this first problem is so important, and you think about the reversible work that you need to do in order to bring them to a separation R, starting from a separation of infinity, that is per construction W of R, right? That is the definition of the potential of mean force. And how did we do that? We had that interesting relation that we showed regarding minus average of du Rn by d R1, keeping R1, R2. This was equal to Kt ln G, right? So this is what we had. So the reason why this is called potential of mean force, because this process is carried out in the presence of all these other particles. In fact, one of them might be in the middle of these 2 over here as they were brought around. And as you do the process of bringing these particles around, all these other particles are going to respond. They are going to do something else. Furthermore, they will have their own probability distributions. For example, if you're bringing these 2 particles close together, the other particles are more likely to be found in a configuration like this versus a configuration that looks like this, right? This is less unlikely. The one on the left is more likely. So the potential of mean force takes all of this into account. So that's all fine. However, if you did not have anything else, if these 2 particles were being brought together in vacuum, then all you are doing is work against their potential energy. So a more natural way to understand potential of mean force is that potential of mean force captures the reversible work that needs to be done against all other, not other is a bad word, all existing forces. So if you have 2 particles in a vacuum that are being brought together, the only force that exists is that potential energy related force, right? And that's why W of R is going to be equal to U of R. If you had other things in the system, then you are doing work not just against the potential energy, but you are also doing work against the solvent, the environment, all these other things that exist in the system. And that's where it will be different. And this was the starting point of our derivation last time, where we said that W of R will be given by U of R plus some difference delta W of R. This is just a definition of delta W of R. This equation doesn't have to be, it's not just valid in the low density limit. This is just whatever is not counted by U of R, you say it's accounted in delta W of R. But the more important thing is that in the very low density limit, you will kind of start approaching a vacuum type environment where the two particles do not experience anything else. So in the very low density limit, W of R will approach U of R, and therefore delta W of R will approach 0. So this led us to the idea that G of R, which is defined as e to the power minus beta W of R. So this is the relation. What was this? This was the relation between potential of main force and reduced distribution function, radial distribution function G of R. So G of R is equal to e to the power minus beta W of R can be written as e to the power minus beta U of R, e to the power minus beta delta W of R, right? This is, so let's call this equation 1. Equation 2 is simply using equation 1. But now this can be, so this is exact. There is nothing wrong here. This is also exact. Now, this was an approximation. And the next equation is also an approximation that we say that e to the power minus beta U of R is therefore going to be something like 1 plus order of density, something that goes as density. There will be higher order terms, but we ignore them. We just care for the terms which are order of density. Once we had this, I'm just rehashing the last part of last lecture, we showed earlier that average energy divided by N, average energy per particle is equal to 3 by 2 kT plus half dr rho G of R U of R. This is why I gave that decoy answer of GU. When you guys become professors, you will see it's so much fun to design decoy answers in pop quizzes. You can give things that you know you have seen somewhere, and some students will go for it. This is kind of semi-sadistic fun. Anyway, sorry. So, but G of R, U of R shows up here. It has nothing to do with the approximate value of W of R. Okay, so this was, what was this? This was E ideal. So this led us to write in delta E over N equal to rho by 2. So the change in total energy with respect to ideal gas is given by this term, right? So delta E is given by this term. That came out to be rho by 2 dr e to the power minus beta U of R 1 plus order of rho. So this is all we did last time. So now we have two relations that we are going to use, which you derived in the homework. Delta E by N is equal to partial beta delta A by N by partial beta. So if we use this thing, here we derived an expression for delta E by N, and here we are saying that partial beta delta E by N by partial beta is equal to the same thing. So therefore, we have partial beta delta A by N by partial beta must be equal to this thing over here is equal to rho by 2 integral dr e to the power minus beta U of R 1 plus order of rho. So now we can bring this partial beta to the other side, and we can write this as integral and then integrate it, partial of beta delta a by n, and here we will have rho by 2 integral partial beta integral dr e to the power minus beta u of r 1 plus order of rho. Where do we integrate it? We integrate this thing from 0 to some temperature beta. 0 to some temperature beta. So this looks abstract, but it's one student wants to enter. I'll let Kevin in. Okay. Okay, Kevin is in now. I'm keeping the waiting room on because in many departments there have been unpleasant incidents, and it's a small class, so I'm going to keep the waiting room on. I know it makes it a bit clumsy. Maybe I can make someone else as a co-host so they can also let people in. I will make Emily as a co-host, and I will make Becca as a co-host, and I will make Ben as a co-host. So if someone else is in waiting room, you guys can ideally let them in. Okay, good. So what does this mean? What does it mean to, so we are integrating here in inverse temperature. Inverse temperature is equal to 0. What does that mean? That means that temperature is equal to infinite. So we are integrating from very high temperature to some finite temperature. And that makes sense because at very high temperature, we expect our approximation. At very high temperature, we expect the density to go very small, right? At very high temperature, we expect that W of R will start to look like U of R. That's why these limits are okay. That's why we are not integrating from infinity to beta, for example, because inverse temperature infinity would mean very low temperature, and we want to stay away from very low temperature, at least in this class, because first of all, quantum effect starts to take role, and secondly, you can have funky business happening. Things are not really ideal gas. So we have this integral that's not very hard to do, and on the left side, you just get beta delta A by N. On the right side, you can bring some of the things inside. We will write it as, so this rho by 2, we will write first. Then we will write integral dr, this one, e to the power minus beta ur, and this one. No, the e to the power minus beta ur we will skip, and everything else we will write, because e to the power minus beta ur still has a beta term over here, so we cannot really remove that. So we will have dr u of r 1 plus order of density multiplied by beta partial beta e to the power minus beta u of r 0 to beta. So this gives us that, and again, I'm gonna go just slightly quickly because this is done in Chandler in great detail, this section, and I wanna really get to next section today, which I think is very exciting. It's one of my top 3 parts from this semester. So what we are doing here is Chandler section 7.4, page 206 or so. I'm not deviating from it. So this thing can be integrated, right? This is a simple integral. This is like dx e to the power minus kx, right? There is nothing profound here. U of r, remember u of r, why is it easy? Because u of r itself does not depend on beta. So it's a strange looking integral because normally when you integrate these things, you have a variable, but here the function itself is a coefficient that you treat as just some coefficient of multiplication. So once you do this integral, what you get is that minus beta delta A by N is equal to rho by 2 dr f of r, some function, plus higher order terms that depend on rho square, where this f of r comes from this integral, and is equal to e to the power minus beta u of r minus 1. So I will write that down again. I wish I had a bigger iPad. Next, if in fall we have to teach again online, then I might get a bigger iPad. So what did we write down? We wrote down minus beta delta A by n is equal to rho by 2 dr f of r plus some things which are order of rho square, second order intensity, where f of r is equal to e to the power minus beta u of r minus 1. So let's see whether this equation makes sense. What would u of r be for an ideal gas? Anyone wants to help me?
Zero.
Zero. Good. Who helped me? Ben helped me. Good. So what would f of r be? E to the power minus beta 0 minus 1 equal to 0, right? 1 minus 1. So what would delta A be? 0 plus order rho square. We are not worrying about that. Does this make sense for an ideal gas? Yes, of course it does, because we are talking about A minus A ideal is equal to 0. So there is nothing profound. It's just fine. So, but at this point, we can use the other relation that you derived in the homework, which is rho square partial beta delta A by n. It looks like a complex relation, but it's not really. Beta P minus rho. If you use this, and let's number our really bad in numbering equations. So that's equation 3. Let's call this as equation 4. In equation 4, we get beta P is equal to rho plus rho square B2 of T plus order rho cubed, where B2 of T is this thing dragging over here. So B2 of T is minus 1 by 2 dr f of r. So, and we have another expression for the second virial coefficient. Now, so this is to be contrasted. So how did we do the, we derived the virial coefficient previously also, right? So we derived it for, if you go to my last lecture's notes, we derived it in this first approach, and we got a term that looks like this. This is beta P, right? Beta P is equal to rho minus rho square by 6 kt something, blah, 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 right? So keep this in mind. Just take a picture in your heads and compare this to this one. Beta P is equal to rho, and we have this term. This term is, it looks a bit different from what you had earlier. But if you go back to what you had earlier and put over here g of r is equal to e to the power minus beta u of r, then you will recover that equation that we just derived. So they are connected. However, this one in principle could be more powerful. You could expand and get the higher order terms and things like that. So this is our second approach of getting an equation of state. Why is this important? Because this f of r over here captures the interaction potential between things for pair potential. So it's our way of dealing with interacting systems. This is all fine, but what I'm going to do next is something I like a lot, which is really powerful. So these methods that I showed you, both of them, are cute. Well, depends on what your definition of cute is. I think they're cute, but they are not all that useful. What I'm going to show you now is extremely, extremely useful. It was first derived by Zwanzig in 1954 in JCP, in Journal of Chemical Physics. I think it was an 8-part paper, and he derives it in the first paper. And this was, I think, when he was a PhD student at Caltech working with Kirkwood. Back in the day, I believe it was quite common for people to do things with their PhD advisor and thank their PhD advisor in the acknowledgement. And that's it, not have co-authors. So these are all like single author papers. Good luck doing that. These days, it doesn't happen that way. So what we are going to talk about today is the free energy, or actually let's call it statistical mechanics perturbation theory. So in quantum mechanics, we spend a lot of time, those of you who have taken it, talking about time-dependent perturbation, time-independent perturbation. You have probably not seen this material. It's quite simple. What the intuitive idea here is that, let's say you have a system made up of lots of atoms, and let's say these atoms are interacting with some spring, okay? They're connected to some springs. And let's say that this spring energy looks something like this. It has a particular K that governs it, half kx squared. Now, instead of this, imagine that they were still connected by springs, but the springs were, I don't know, a bit looser. What does that mean? A looser spring, how would it look like? Should I draw the curve in here, or should I draw the curve in here? It should be the second one, right? A looser spring allows it to go outside, back and forth a lot more. So let's say the spring is just slightly looser, and it looks something like this. Now imagine that the spring is even looser, so loose that it starts to look like this. So you could imagine that, so the difference between this one and this one is huge, right? Actually, I will use a different color. The difference between the black and the blue is huge. But the difference between the black and the red is not all that much, right? It's a small difference. However, so the question is, do the thermodynamic properties, so in a more formal setup, let's not go into formal actually, let's think about intuitive way. So the question is, could you calculate the properties of the system using this red potential, the red interaction, and still be able to say how it would have behaved in the black potential? Intuitively, you can see how it is, right? You would say, well, in the red one, it's going to oscillate a lot. In the black one, I'm just going to say, let's scale down the oscillation slightly, right? The overall oscillation will be a bit less. So you could imagine a case where you go from the blue one and talk about changes in some potential that looks like this. From that, you go to some other potential that looks like this. From that, you go to some other potential you look like this. And through a ladder, you move all the way and go from here to here. And why stop with the blue one? Why not start with an ideal gas where there is simply no interaction? Could you think of perturbations going from an ideal gas all the way and talk about what happens in the system with interaction? So this thing, this statistical mechanics perturbation theory, which was introduced in 1954, is being used enormously in drug design, and that's the context of this one of the 3 papers that's assigned for midterm. It's called free energy perturbation method. One of the companies that supports my lab, Schrodinger, they have a software made of it, free energy perturbation. It sells for, I don't know, something like $100,000 a year for a single license or something like that. It's heavily used software that, and other groups also have similar methods. So in drug design, where it would be important, let's say you have 2 residues that have strong Coulombic interaction, right? You have a residue where you have a strong positive charge and the other residue has a strong negative charge, and you have to worry about that complicated Coulombic interaction. But instead of that, you start to think about, well, what if we don't think of the full positive charge, we just think of some fraction of this positive charge, eta multiplied by plus and eta multiplied by epsilon, negative. Then the interaction would be a bit less. And again, you could imagine scaling the eta from 1 to 0. So you would have a system where there is no interaction charge. So for example, you could have an alanine residue where there is no interaction energy, and going all the way to some charged residue and try to see how these modifications happen. So I will derive the math for this. I will show you how it's useful, and then I will tell you what are the challenges in actually using this in practice. Well, the biggest challenge is that you have to have some overlap between the 2 potentials. And let's see what that means. So let's look at this in a formal level. So we will think of our total potential energy. Let the total potential energy, I'm going to call it as U, discrete n. So what is this? This total, for example, this could look like pair potentials, I more than j more than equal to 1, small u of rij. But this u of n is a function of Rn. So I know it's a bit confusing that I'm using a capital N in subscript here, but there is a reason, because I want to keep the superscript for some other things. So let this total potential energy be decomposed in the following form. Let it be given by un for some reference system, like the analogy that I drew over there, for some reference system. So actually, I will use a different color, UN0. The reference system also has all n particles. It's just that the potential is a bit different. Plus some other potential, un1 of Rn. So for example, if you had this one and your reference system was something like this, then the perturbation would be given by this gap in between them, right? So this quantity un1 could be very large. There is nothing stopping us from it being very large, but we will think of the case when it is a perturbation. We want un0 to be close enough to the true un, but just slightly different, okay? That's when all of this will work, and you will see why it matters that un1 should be perturbation. But what we have written down so far, it really doesn't make a difference. It could be a small, it could be a large number, and nothing stopping it, the theory to work from in that case, but it will just be it will be a useless theory. So this un0, the reference potential, could be a system made of hard spheres, could be a hard sphere system. It could be ideal gases. It could be anything that you want to pick. There's no problem with that. Let's think about the partition function though for the true system. The partition function for the n particle system, how do we write it? That's given by, again, I'm not talking about the momentum coordinates. It will be given by dr1 rn e to the power minus beta u n, right? That's the definition of the partition function. That's one formula that at this point in the semester you should not be unhappy about. It should be your best friend. Now we can use our, what's the number of this equation? Equation 4. Let's call this as equation number 5. Equation 5 says that un is equal to un0 plus un1, right? So let's just do that over here and write it as un0 plus un1, okay? So this is fine, but now let's do something that will seem trivial, but it will lead to a very beautiful relation. And that's the very nice thing about Zwanzig's thing. The derivation is like the opposite of, it's the most useful relation that you will see in this class probably for now. It's also the easiest to derive, which is incredible. What we are going to do is to take this thing and multiply and divide it by the same thing. We can always do that, right? We can multiply and divide it by 5 or 8. We can do multiply by 8, divide by 8, multiply by 80, divide by 80, multiply by 480, divide by 480. No one's stopping us from doing that. In this case, we are not going to divide and multiply by that. We are going to divide and multiply by Zn for the reference potential. Okay, so this over here was the Zn for the true potential, and this is Zn0 is the partition function for the reference potential. Okay, how's that going to look like? let's keep this Zn0 over here on the left-hand side, and let's think about these two things, this one and this one. How will that look like? The top one is going to be the same. We will not do anything profound there, except one slight change that will become obvious in a moment. We will write this minus beta un0 and e to the power minus beta un1. Instead of summing it in the exponential, I have written down the two exponentials separately, okay? And now I will write down the Zn0 as dr1, drn. What should we have here in the power? I'm stuck, I need help. For Zn, we had un. What should we have for Zn0?
un0.
Un0, exactly. So this will be, who was that? Who helped me? Shokan. Oh, good. You're there. Very good. So perfect. So that's un0. Now look at this thing. It has a very interesting form. Forget about un1 completely and think what is the meaning of dr1, drn e to the power minus beta un0, some quantity f, I don't know what is f, some quantity f which depends on all particles rn, their position, divided by dr1, drn e to the power minus beta un0. Have we seen something like this before? What's a shortcut for this quantity?
That's the average.
Yes, that's Suhas, absolutely correct. That is the average of f subscript 0. It is the average of f calculated in the reference potential, right? What does this mean? This means that this equation over here is Zn0 multiplied by e to the power minus beta un1 calculated in the reference potential. And that's one-Ziggs relation. Let's write it down once again. So what we showed is that Zn for the true interaction, for the true system is equal to the partition function of the reference system multiplied by average value of e to the power minus beta un1. This is the perturbation. This is the difference that you have from the reference system calculated in the reference system. This relation is what Zwanzig derived for the first time in 1954. Currently, I know of my friends who are professors at multiple places. John Chodera is a professor at Sloan Kettering, and Greg Bowman is a professor at Washington State University, WashU in St. Louis. These people run a calculation called folding at home. Folding at home, you can go and check it out. It's a massive effort. It was recently covered by Forbes magazine, Wired, this or that, whatever. What it does is to take your computer when it's lying idle and runs lots of simulations there, okay? And then it patches these simulations together to calculate the overall property. This type of calculation is perfect for folding at home. You could take a reference potential here, a slightly different reference potential here, a very slightly different reference potential here, and so on and so forth. And you can calculate all sorts of things. Currently, they are using folding at home to design drugs for COVID-19. And it's this formula put in work. That's the key of it. There are lots of other advances that have gone into it, but this formula is currently help us come up with drugs to target COVID-19. So before we go into that, so let's look at this formula once again and write down things, what they are. So this is the partition function. And again, only configuration. We are ignoring the momentum part, sorry. Partition function for unperturbed or reference system. And this one all of this is average calculated in the unperturbed system. So you're not doing any calculation in the perturbed system. All calculations are being done in the unperturbed system. So now you can see why there will be a problem. Why would we have a problem if UN1 was, or actually UN, the true interaction UN was very different from UN0. So let's say, so what was our equation? We said that UN is equal to UN0 plus UN1, right? This decomposition is general. You could have any UN1. But let's say you have a case where UN is much larger than UN0. Okay, so what this would mean, what would this mean about UN1? This would mean that UN1 is much more than 0, right? The perturbation that you have. So in our very important equation that we are going to number equation number 7, why would this lead to a problem? Because now you are calculating e to the power minus beta UN1. And if UN1 is very, very large, this thing will become a very, very small number. It will start, before you know it, it will start to approach 10 to the power minus 18, which is computer 0 or even smaller numbers. And you have a problem. So that's why UN1 has to be small. But the way typically these simulations or these calculations are done in practice, we are going to apply it to something that we can do analytically, and that will give you intuition. In practice, the way it is done is to think of UN made up of some UN0 plus UN1, keeping this at small, and then actually, I'm going to talk about how it's done in practice later. Let's just look at it in our, let's look at it for a simple system and see how it looks. So for now, we will assume that UN1 is much smaller than UN0. Okay? Because if we didn't do that, calculating this average in the brackets will be extremely difficult. It will be such a small number that you won't get it to converge. So let's assume this is true. So what's our famous formula? I like this formula so much, I will write it again. This is a wonderful formula. Zn is equal to Zn0 e to the power minus beta UN1 calculated in 0. It's almost like the true partition function is a product of the unperturbed partition function and plus something that is like a partition function for the perturbation. Something that is like a partition function, but that something is complicated. So in general, e to the power minus beta UN1 in the unperturbed partition potential can be written as, we can expand the series. It will be 1 minus beta UN1. So Luke, you were talking about series, and so this is different from Sommerfeld. This is yet another type of expansion. That's why I wasn't sure how to answer your question. So, and what did I, okay, so let's first expand inside the bracket. E to the power minus beta UN plus beta square by 2 UN1 whole square minus blah, blah, blah. All of this calculated in the actual partition, in the reference partition function. And what does it mean to calculate in the reference partition function? It means this thing. So now we can write it down as average of 1, that is simply 1 minus beta, and we are working in a canonical ensemble, so the beta average, it's a well-defined temperature, average of UN1 calculated in the reference potential plus beta square by 2 average of UN1 squared. Funky notation, but the thing to keep in mind is, what does this mean? This means average of UN1 multiplied by UN1 calculated in the reference potential, plus other terms that we are going to ignore because we have assumed that UN1 is very, very small, so it won't be a huge difference. This is fine, but the main thing that we want to do here, so where am I taking you with all this? Where I am taking you with all this is to think about thermodynamics of the of the true system, because the reference potential also can be interacting. It just will be a different type of interaction. We want to think, so actually let's write it in red, because this is, what is the big picture here? The big picture, or the big question, is how do we express the thermodynamics, thermo D, of the true system in terms of the thermo D of the reference system. That's the question we are trying to answer. What do we mean by thermodynamics? Well, all sorts of thermodynamical observables. For example, so I lost my page numbers. This was page number 7. This was page 8. So we know that UN is equal to UN0 plus UN1. So, but potential energy is not thermodynamics, right? Because potential energy is missing one crucial thing that makes all of thermodynamics and statistical mechanics really complicated. It's entropy, right? It's missing entropy. It's all about the entropy in the end. So potential energy does not contain that. What I am asking you is, how about the Helmholtz free energy? How would the Helmholtz free energy for this system be related to the Helmholtz free energy for the reference system? What would be the connection here? What would this look like, for example? That's what we want to calculate. So how do we do that? So how do we get Helmholtz energy of true system from Helmholtz energy of reference system? And you can see why this might be useful. If your reference system is a hard sphere, you could calculate, or an ideal gas, it's easy to write down the Helmholtz free energy for the ideal gas. Why is it easy to do that? Because it's easy to write down the partition function for the ideal gas. So if this correction term is easy, then we could just calculate the Helmholtz free energy for the reference system and then directly get the Helmholtz free energy for the true system. So how do we do that? So for that, we realize that A is equal to minus KT ln Q, right? Helmholtz free energy is the log of the partition function. Q in turn, and now the thing to keep in mind is that so far we have not been dealing with Q, we have been dealing with Z, which is the configurational partition function. So Q itself is given by Zn. Am I using it in subscript? Yeah, subscript. I'm going to mess up my subscript and superscript at one point. It's bound to happen. N factorial for distinguishability or indistinguishability divided by lambda 3, right? This is very generic. This takes care of the momentum program. So what does this mean? Therefore, minus beta A is equal to plus log of Q is equal to log of Zn by n factorial lambda not A lambda 3n. What can we do here? Here we can use equation 7. So let's call this equation 8. Use 7 in 8. What was 7? Again, I like it so much, so I'll write it down again. 7 was Zn is equal to Zn0 e to the power minus beta un1 calculated in 0, right? So we can put this in the place of this thing. What will we get then? Therefore, equation 8 implies that minus beta A is equal to ln of Zn naught by n factorial lambda to the power 3n plus ln of average of e to the power minus beta un1. This is like so close yet so far, right? When you look at this ln of average of e to the power minus beta u, this is one of those moments when you are in an in-class exam and you have 10 minutes remaining. You just say like, how about I just switch my average with the exponential and my life would become so wonderful because log of exponential would be 1 and everything would disappear and I would just be there with un1 and voila, everything is done. Sadly, it's not that simple. You have to calculate the exponential and then take its average, which is completely different from calculating the average and then taking the exponential. And if you think that I'm talking abstract garbage at this point, the number of times the exponential curve has shown up in the popular media in the last 1 month is at an all-time high thanks to coronavirus. So these things matter. Don't average your exponentials in a casual manner. These things make a difference. So that's complicated, and we are going to get to that in a moment. How about this one? Can we say something about this thing? That is minus beta A naught. If you ignore all this business on this side, if you ignore all of this, this is Zn naught by n factorial lambda to the power 3n. This is the Helmholtz free energy of the reference system. So that's quite nice. So now we have, I think, hopefully you agree. So that means that we have just shown that minus beta A is equal to minus beta A naught. And I should use this in this superscript, minus beta A naught. So by the way, this material that I'm doing right now is not in Chandler's book. It is given in Macquarie's book. It's chapter number Macquarie, chapter 14. Did I get it right? 14.1, statistical mechanics perturbation theory. That's where he talks about it. And even he does mess up his subscript and superscript, which is annoying. Yeah. So I'm going to follow Macquarie's notation, and Macquarie uses this as A0. This is Helmholtz free energy of reference system. I would have used superscript, but I'm just going to be consistent with Macquarie. Minus, what did we have here? We had plus actually ln of average of e to the power minus beta un1 calculated in this thing. So we can think of this as minus beta A is equal to minus beta A naught minus beta A1. So A1 is our perturbation free energy. So now we have almost done what we wanted to do. We wanted to calculate this term over here. What was it? And we have kind of an expression for this. But this is, let's see if we can simplify it further. So this we will call as equation 10. So On its own, equation 10 is fine. You know the value of the perturbation in the potential energy, so you can go and calculate it, but let's see if we can simplify it a bit further. So the next part is a bit mathematically, it's not complicated, but we are going to compare two series with each other. Let's just power through it. So, and again, Macquarie 14.1 is what talks about this. So we want to expand A1 as a power series in beta. Why in beta? Because we want a series that is valid for low beta or high temperature. We are not going to expand it in the powers of T, but in the powers of beta. So we are going to, and what does power series mean? It's just a fancy way of saying that we should be able to write something that looks like this. N is equal to 1 to infinity. Some coefficients, Wn by n factorial, minus beta, n minus 1. So this is called a power series. Such a power series is valid in general. It will be valid at any beta, but the problem will be that this will be valid at any beta, so any temperature, if you are willing to consider all W's, right? W1, W2, W3, W4. If you're willing to consider all terms in the series, you can come up with as accurate of an expansion as possible. We want to consider something which is valid if we want something valid only for small beta, that is high temperature, which is the limit for classical things, then we could get away with first few terms in the expansion. So let's try to calculate that. And before we do that, I just want to make a point that modern day uses of Zwanzig's perturbation theory do not go down this route. They stay with this formula in the square bracket, in the rectangle. And instead of going through all this analytical stuff, they just use computers to calculate it. They use a system where the interaction potential is the reference potential, and then go and calculate this through brute force. And that's what the thing I was telling you about the coronavirus, where they are using ideas like this, where you have a ladder of interacting systems. You don't do it in one chunk, because if you just want to do it in one chunk, you will need to have the perturbation to be very small. So you take the true potential, you think of a reference system where there is a slight difference. And then you think of another reference system where there is further slight difference, and you break it into chunks. The nice thing is this can be done in what is called in computer science as an embarrassingly parallel manner. So the different computers don't need to talk to each other. So you can do it in a distributed computing framework where all computers over the world are doing this calculation in parallel. Every computer is thinking about two systems at a time. One system and another system slightly apart up from it. But when you patch it all together, you can calculate the properties in principle of a complicated drug that is trying to go and bind to some complicated protein. And at the other end, you have an ideal gas where there is no interaction. But in the middle, you have a bunch of small perturbations. And then you patch it all together using this formula, and you get the final property. Here, we are not doing computers, we are doing it in an analytical way. So this is what we need to calculate. So we are going to now calculate W1 and W2. So this equation 11 can be written as, if
we can't see anything that you're writing.
Oh yeah, sorry. Why did that happen? Yeah, it stopped moving. Thanks for pointing there. Yes. Right?
Yes.
Okay, great. So now let's take an exponential of equation 11, both sides. So e to the power minus beta, if you thought it wasn't complicated enough, well, let's exponentiate it, is equal to e to the power n is equal to 1 to infinity Wn by n factorial minus beta n minus 1. So this is equation 12, but we have seen e to the power minus beta a1 in some other form. Where have we seen it? How did we introduce beta a1? We introduced it by writing this form. So now if you look at this equation carefully, what this is telling us is that e to the power minus beta a1 is equal to average of e to the power minus beta un1 in the unperturbed ensemble, right? That's just definition. So this thing must be equal to, it's equal to both of these things. It's equal to exponential of this, and it is also equal to exp of minus beta un1 calculated in the unperturbed ensemble. And the only business that remains now is to expand both of these and compare them term by term. That's all we need to do. So if you are going to just stop at W1, you can see how it's going to look like. What is, so for example, okay, and we will stop some. So what, I will write it down again. So what we have shown so far is that e to the power minus beta a1 can be given in two ways. It is equal to e to the power or exp of minus beta un1 calculated in the unperturbed example. It is also equal, and what is this? This thing is summation k is equal to 0 to infinity minus beta to the power k by k factorial average of un1. I've just written it down explicitly. So that's one way of writing it, and it can also be written as exp of summation n is equal to 1 to infinity wn by n factorial minus beta n. So the way this works is to write it down explicitly and compare W1 and W2. It gets very complicated already at W2. I'm just going to show you how to do W1, which is quite simple, and it will give you a flavor. So what does W1 mean? If our world was stopping at W1, then the red one would, let's stop at W1. The same picture applies for W2. Let's stop at W1. So what would this mean? This would mean that this series is e to the power. We don't have a summation. We are stopping at the first term. So W1 by 1 factorial minus beta, right? So we are interested only in the, remember our whole power series was for terms in the power of beta. So we are interested only in the first term in beta. So if you compare it to the thing in black and you stop only at the first term in beta, am I missing something?
I thought you had said that it was minus beta to the n minus 1.
Yeah, but good point. But remember, we multiplied by a beta. So I messed up something there. So here, if I multiply by beta, that's making my life messier, right? So you're right. So this was wrong. This should be minus beta n. Yeah, thanks for pointing. So this is minus beta n. So if we want to consider that, we have to go up to, okay, let's start at this point next time. Let's quit when we are ahead. So today, the equation that you should think about is this equation that we derived for connecting the partition functions. And what we started doing that, I gave you a picture of why it is important, but then the problem we are trying to solve with it is how to calculate the thermodynamics of the true system in terms of the unperturbed system. In order to do that, I wrote down the Helmholtz free energy, and I got a term for the Helmholtz free energy for the reference system. And then I have a perturbation from the Helmholtz free energy. and I'm trying to calculate this perturbation in the limit of small beta, that is high temperature. And I'm almost there, but I'm missing something in the algebra. So we will continue here next class. Once we do this, the other thing we are going to do is to put it in practice and use this expression when we think of U of R, this is the small u of R, as hard spheres. So some generic U of R, we will decompose it when the reference system is hard sphere and some perturbation R. And from this, we will again derive our van der Waals equation of state. That will be the end of classical fluids, which we will finish next class. And then we will move to phase transitions. We will talk about Ising models, which are a bit different from what we have done so far. And we will talk about Ising models and mean field theory, and which should be a lot of fun. Okay, so see you on Thursday.